Uh, I just sent out the solutions to chapter 6.
Yeah.
I don't know if you've gotten. Okay, good. You have gotten it, and so that's very good. And let me just take a little while to finish up on discussion on the application of the group SO3, three-dimensional rotations, to rigid body dynamics. That is how to describe a particular rotation. There are two ways of expressing the theorem. The one we proved last time was describing a particular rotation in terms of a set of space-fixed axes. Okay. The second one, which is the one that's more commonly used in classical mechanics texts, including the one that you are using now, is to describe the rotations in terms of the moving frame that is attached to the body. Okay, the body fixed. And we can prove the second mode of description in terms of the first mode. So let me just recall that for you first. Euler's theorem. So let's say you have a set of space-fixed axes. This is called epsilon 1, epsilon 2, epsilon 3. And you imagine some rigid object that is doing a rotation. But we will describe the rotations with respect to the axes in this space-fixed set. And Euler's theorem, so this is space-fixed. So Euler's theorem basically says this. That any rotation, I'm going to say that this is an element in the group SO3. Any rotation can be expressed as a succession of three rotations. The first one is about the third axis by some angle psi. And the next one is about the second axis by some angle theta. And then finally about the third axis again by an angle phi. Okay. So you imagine that you start off with the rigid body, in some way. Okay. And your rigid body is supposed to go through a rotation, any rotation whatsoever. Whatever that is, you can always represent that rotation as a succession of these three, with this one first, this one second, and this one third. So, and remember, in this way of writing, third means with respect to the third space-fixed axis, 2 in here means with respect to the second space-fixed axis, and then finally again 3 with respect to the third axis, and so on. So that you can imagine the rigid body rotating about 3 by some angle psi, and then rotate about 2 by some angle theta, and finally rotate by 3 again by some angle phi like that. Okay? And the proof of this theorem, which we did already last time, so I won't repeat it, was based on this very important, I think I called it a lemma in the book. A lemma relating isotropy subgroups. So that isotropy subgroups are always characterized in terms of a particular point in the manifold. Okay, so the isotropy subgroup of SO3 corresponding to a particular point x in the sphere is a group of all those rotations which would leave x invariant. And then you imagine a rotation g, which would take you from x to gx. Okay, and then the isotropy subgroup relative, or with respect to that different point, is a different isotropy subgroup. One which leaves x invariant, and the other one which leaves gx invariant. And the two are related in this fashion. Okay? And so using this lemma, we were able to prove Euler's theorem like this, expressed in terms of space-fixed axes. Okay? Now, Euler's theorem can also be expressed in terms of a set of body fixed axes. So let's say you start off with a rigid body in some orientation, and you choose a particular set of body fixed axes. So you describe a rotation with respect to that set first. So the body has been rotated somewhat, and then the next time you describe the second rotation with respect to one of the new body fixed axes. So then the body rotates to some other position, a different set of, it's always body fixed, okay? And then finally you describe it with respect to a third body fixed axis. And so let me write it down first. Let me actually draw the, I think I did this last time, but let me do it again, okay? So Euler's theorem with respect to body fixed axis. So you start off with some axis. Let's say this frame is kind of nailed to the rigid body, so it's body fixed. And at first, I think we call this E1, E2, E3. The first step is the rotation about the third axis also. Now, by this angle, okay? So by the angle phi, let's say, okay? So this is a first step, okay? So the rotation then is again represented as a product of three successive rotations. The first one is about axis E3, so by the angle phi. So I'm simply going to write it like this. And then the second step, wait a second. So let me actually try to be clear in here. So by this rotation, which I'm going to call R3 phi, okay? And so the frame will have changed a little bit, right? So if you rotate it about the third axis, E1 will then be going over somewhat by an angle phi, and then E2 will be going over by the same angle, and so on and so forth. So let me draw the picture this way. The third axis is still the same after this rotation because it's rotating about that axis. Let's say the original E1 is like that. The original E2 is like that. The new E1, which I'm going to call E1 prime, will be like that. So this is the angle phi, right? Where's the new E2 going to be? Of course, it's going to be this one, and then displacement from the original E2 by the same angle phi also. Okay, so this is after the first step of rotation. This is, so let me call this E2 prime. All right. Now, so I've done one, right? So the next one will then be rotation about the 2' axis, which is rotation about this one by some angle theta. Okay. Now, so you are doing a rotation about this new axis, like so. Always consider rotation in the positive sense if theta is positive by some angle theta. Okay. So now you try to see what is the new set of axes going to look like. It's going to look like this. This time the E3 will be changed. So the original E3 is like that. Let's say the original E1 was like that. The E1 prime was like that. And this is E2, let's say. E2. And the E2 prime was like that. Okay, so this angle phi here, this angle phi here, okay? Now, the thing is you're rotating about this. you're rotating about this, so therefore E3 will move down, and then E1 prime will move down also, right? So after this step, my moving frame will be like this. So let me call this the new E3, which we're going to call E3 prime, and then the new E1. I've used up the names E1 and E1 prime, so let me call this E1 double prime. Like so. And I'm rotating by an angle theta, so therefore this is angle theta in here, and I'm coming down here like so, so this is angle theta. Diagram becomes a little bit more complicated, but I hope you understand what we are trying to do. Okay? So at each stage, I have drawn the final orientation of the body fixed axis as solid lines. And all the previous ones which had been rotated represented by dotted lines. Okay? You start off with that, then that, then that. Okay? So the second one is rotation about E2 prime by an angle theta. So the second one is rotation about 2 prime by the angle theta, which we have just drawn. And then the last one is rotation about the 3 prime axis, which is this one, by the angle psi like that. Okay? And let's see what we're going to end up with. So this is the E3. This is the E3 prime. Now the E3 prime is not going to be changed because this last step you're rotating about that direction, right? So this is, I'm going to still draw this as a solid line. So let me just go like this in here, and then this one will be the original E1. This one will be the E1 prime. This one will be the E1 double prime. Go to the second, yeah, E1 double prime. E1 double prime, right? And okay. So I am now the E2 prime is this one in here. So E2 prime, let me draw this as a dotted line now. This is E2 prime, okay? So at that step, I'm left with this one, okay, at the previous step. Wait a second, what is this? Sorry, this line is not meant to be there. I can't get rid of it, okay? So the last step, I'm going to be rotating about this direction again by some angle psi like that, okay? So as a consequence, you take a look at this plane, okay? So you rotate about this axis by some angle psi, so I come over here, this will be my final orientation, right? So I'm going to call this E1 triple prime. That's a final one. And then E2 double prime. Okay? At each stage, at each diagram, the solid lines represent the final configuration of the frame after rotation. And the statement is that the same R that I have expressed using the space-fixed, using rotations about space-fixed axes, can also be expressed as rotations about body-fixed axes in this manner. So finally, the last rotation is about 3 prime, E3 prime, by the angle psi, okay? And take a look at one interesting thing in here. If you choose to express the rotation with respect to the space fixes, 3, 2, 3. With respect to the body fixes, 3, 2 prime, 3 prime, with the axes labeled in that manner. But the interesting thing is that the angles are reversed, okay? So it goes from psi theta phi, in this way, it goes from phi theta psi. So whether you choose to express it with respect to the space fixed frame or the body fixed, it's the same set of 3 angles that are involved in describing a particular rotation, and those 3 angles are the so-called Euler angles, okay? Those of you who either have or are taking my classical mechanics course, we'll be studying that a little bit later on in the course to study the rotations of a rigid body, especially the asymmetric top using these 3 different Euler angles. So far in classical mechanics, we haven't done so yet because we're using the Euler-Poisson's equations, but later on we can use another approach called the Hamiltonian formulation, and it's much more succinctly expressed in terms of as a set of equations concerning how these angles change, okay, for rotation. So the final step is to prove to you that, in fact, you can express it like this in terms of knowing that we can express it like this. We're going to prove that you can express it like that. Also, so the 2 modes of description, again, one with respect to the space fixed frame, and the other one with respect to the body fixed frame, are entirely identical to each other. Okay. So this is what we are going to try to show you. All right. Okay, so our procedure of showing this is show that this is equal to that. Okay. Again, the main thing to use is this isotropy group lemma here. Using that, it can be proved rather easily. Okay. Okay. Do you need to leave those diagrams there so that you can refer to it while you're looking at a proof? I'll try to leave them there first until I run out of space. So let me take this element first, R3 prime psi. And you remember this is a rotation about this axis in here. It's a rotation about this axis in here. So yeah, this is a rotation about this axis by this angle psi in here, okay? I'm going to try to relate it to, let me write it in a different way. 3 prime was obtained by rotating 3 to here, about the 2 prime axis by an angle theta, okay? Obviously, this vector is obtained from that vector by rotating like so, about the 2 prime axis. So I'm going to write this axis as the action of rotation about the 2 prime axis by some angle. All the stuff in the subscript in here. This represents a particular element in SO3. That element, which is rotation about the 2 prime axis by the angle theta, so rotating about this axis by psi. You see how we wrote it? Okay. Now, so there's a rotation which got you from this point to this point, because both points can be thought of as points lying on a unit circle, a unit sphere, because all these are unit vectors, right? So they all have length 1. So all these tips of all these different axes are all points on the same unit sphere, 2-dimensional sphere. And there's a rotation which brought you from this point to this point. And this is the rotation that we are talking about. Okay, so think of that as G. So the left-hand side is what we have written down here. And then the right-hand side of this lemma allows us to write this as G times the rotation about this axis times g inverse, like so. Let me write it down first and see if you agree with me. So I can write this as r2 prime theta, then rotation about the third axis, which is this one, by psi, and then finally the inverse of this rotation about the 2 prime axis. And this equality is obtained by making use of this lemma. Is that okay? All right. G H G inverse. This is something in the isotropy group of this point, which is this guy in here. All right. This guy right here is something in the isotropy group of this point. All right. And so this lemma allows us to write this equality in here. I'm going to do the same thing with this element by applying that lemma again. So I'm going to write R2 prime theta. Now, what is R2 prime theta? R2 prime theta is this rotation, right? And that 2 prime I can write as R of R3 phi acting on E2, and then rotating this by theta. You see what I'm doing here? Which is the 2 prime axis? The 2 prime axis is this one. How was it obtained from E2? It was obtained by E2 by doing a rotation about the third axis. So the 2 was brought to 2 prime like that. Okay? So, and that was the rotation. R3 phi was the rotation which brought E2 to 2 prime. So that's how I'm writing it. Okay? And again, in exactly the same way, I can use this lemma. So this thing in here would be the isotropy group at this point, okay? And the rotation which brought me from E2 to 2 prime was this R3 rotation. So I can then write this as R3 phi, and then R2 theta, R the inverse of R3 phi, in exactly the same way, okay? Using this theorem in here. Now, I'm just going to put things together. I am going to put this expression for R3 prime into here, and I'm going to put this expression for R2 prime in here and see what we get, okay? It's very straightforward. So then, let's go. So then I can write, take this expression in here, R3 prime psi, R2 prime theta, R3 phi. First going to use this expression for R3 prime psi, which is this whole thing in here. So I have R2 prime theta, R3 psi, R2 prime theta inverse. That whole thing is for this first term, okay, using this expression in here. Now I'm going to use this expression for R2 prime, okay. And so I have R2 prime. Wait a second. Yeah, R2 prime theta is equal to that. Yeah. missing something in here. Well, let me write the rest of the stuff. Oh, actually, let me just write this because there's a cancellation here, okay? Let me just write R2 prime theta R3 phi. And so conveniently, these two collapses to the identity because one is the inverse of the other, so that I have R2 prime theta R3 psi. It's just the identity. And then I just have R3 phi like that. Okay. And the last step is I'm going to make use of this expression for R2 prime and stick it up front over there. Okay. Let's see what we get. We are then going to get R3 prime, R3 phi rather, R2 theta, R3 inverse of phi, so much for this thing in here, and then I have R3 psi, R3 phi. Is that okay? Using this expression for this R2 prime in here, like so. But now let's take a look at these two in here. These two are rotations about the same axis, so they commute. Okay, so I can change the order, and so I can write R3 phi, R2 theta, R3 psi, R3 inverse phi, R3 phi. Having written it like this, I now see that these two collapses to the identity. Okay, and so what I'm left with is just what we would like it to be. The rotation expressed in terms of the space-fixed axis, which is precisely this expression in here. Okay. I suppose you could have gone the other way also and proved that one is equal to the other. And so this way, we have proven the so-called very important Euler's theorem concerning rotations in three-dimensional space. That you can either express it like this with respect to body fixed frame, or you can express it the other way with respect to, space fixed, or with respect to the body fixed frame. Okay. In most classical mechanics textbooks, you see a discussion carried out in terms of the body fixed frame because the body fixed axis is a very convenient set of axes to use in the classical mechanical description of the rotations of rigid bodies. Okay. As we have seen in our classical mechanics classes. But even in quantum mechanics manipulations, well, actually in quantum mechanics manipulations, you can use either way, okay? But as long as you know that they're the same, it doesn't really matter which way you use. Okay, so that ends this chapter in here. I haven't really gone on to discuss the complete theory of representation theory of the rotation group, which is in itself a very, very important topic. I just don't have time to do that. The results will be very, very important in quantum mechanics. Some of you who have been in quantum mechanics classes knows that is sort of incorporated in the algebra of angular momentum operators, the non-commutation relations between Lx, Ly, Lz, and so on and so forth. And so then for a system with spherical symmetry, so that the relevant group is SO3, such as the hydrogen atom, for example, the Coulomb force is spherically symmetric, so you have this rotational symmetry, and so that you can classify all the energy eigenvalues in terms of the eigenvectors of the angular momentum operators, okay, and so on and so forth. What is of importance there is the use of those angular momentum operators and the Lie algebra relations that they satisfy. In other words, the particular structure constants for the group SO3. That is all that is required to demonstrate all those results in quantum mechanics. what we're going to try to do next is illustrate the use of SO4 also in the hydrogen atom. SO4 is a bigger group than SO3, so obviously, aside from spherical symmetry, the Coulomb problem has some additional symmetry, which gets manifested in how the group SO4 is being used. The end result of this exercise is to use the symmetry properties of SO4 to find the energy eigenvalues of the hydrogen atom. In other words, show that the bound state spectrum of the hydrogen atom is proportional to 1 over n squared, where n is some integer. You recall that result, okay? You recall the result for the hydrogen atom is something like this. I think some of you have taken the quantum mechanics, upper division quantum mechanics courses here, but all of you should have taken the 235, I believe, in which the result that I just mentioned, namely the values of the bound state part of the spectrum, is studied. So you have this hydrogen atom, and you represent the energy spectrum like this. This is the continuum. Let's say this is the continuum. Is you give it some reference value. Let's say total energy be equal to 0 is a continuum. That means above this level, energy can assume continuous values between 0 and infinity. But then the bound state energies must all be discrete. Okay. That is the meaning of quantization. Well, that's the result of quantization. One result is that all the bound state energies are quantized, and it goes like this. There's a lower state in here called a ground state of the hydrogen atom, okay? And then you step up, first excited state, and so on and so forth. They get closer and closer to each other until when they get close to 0, they're in, well, it's sort of infinitely dense, so to speak, but still discrete. Remember that result? Okay. We use a set of quantum numbers to characterize these energy levels. The ground state, obviously, is called n is equal to 1 level. And then the second state is n is equal to 2, n is equal to 3. And it can go on to n is equal to infinity because the end result that we are going to try to demonstrate goes something like this, that E is equal to, for the bound state, actually this goes for a hydrogen-like atom, not just a hydrogen atom. Let me write it first, and then so you're talking about an atom which has 1 electron, but which has a nucleus with atomic number Z, okay? So it can have many positive charges, but only 1 electron. Since there's only 1 electron, it's called a hydrogen-like atom, okay? If it were hydrogen, there would be Z is equal to 1, okay? You take the helium atom and strip 1 electron out from the outside, then it's a hydrogen-like atom also, because there's only 1 electron orbiting the nucleus, which has a positive charge 2 times the electron and of opposite sign, and so on and so forth, okay? So the bound states of these must be, you can think of classically as the electron orbiting the nucleus in some way. Of course, quantum mechanically, it's not quite like that because the electron behaves like a wave also, so you use what's called wave function to represent a particular state and so on and so forth. But if you take a look at this result in here, the ground state is when n is equal to 1, and obviously n can go to infinity without ever reaching E is equal to 0, right? Like so. n gets to be bigger and bigger, the absolute value of E gets to be smaller and smaller and smaller. It approaches 0 as n goes to infinity. That's why they're infinitely kind of, these are called, the ones that are close to the, this is called the ionization level, by the way. It's called the ionization level because once you give that much energy, then the electron is ready to be ionized. It means that it gets outside of the attractive realm of the of the nucleus, so to speak. Okay. In the case of a single hydrogen atom, this is about 13.6 electron volts, all the way from the ionization level to the ground state. So when you talk about chemistry, it's energies of that kind of order of magnitude that are involved, on the order of electron volts. When you talk about nuclear physics, there's energies of about 1,000 times that are involved, and so on and so forth. Okay. Now, those of you who have taken quantum mechanics, the upper division class, right? A couple of you here have done that. You have seen this derivation, and it's given in Griffiths also. And the way that it's usually presented is through the solution of the Schrödinger equation. Let's write down all that complicated business, separating the wave function into the radial part, into the angular parts, and so on and so forth. And then, you know, you write the Hamiltonian in terms of the angular momentum operators, and then you find all the energy eigenvalues, blah, 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 and so on and so forth. Out comes a very complicated kind of a story. Part of the result is this, okay? Part of the result is this. But it's not only that. There's a whole bunch of degeneracies in here, which means what? Which means that each of these levels is degenerate. It means that there are different quantum states corresponding to the same energy eigenvalue. And you remember what the degeneracy is for each value of n? It's related to n, but not 2n plus 1. It's 2n squared. Okay? Now let me explain to you, just sort of a little refreshing memories in here. Why is it 2n squared? You see, because of spherical symmetry, there's a whole bunch of different angular momentum states that has the same energy. Those have to do with the orbital angular momentum quantum number L, and then the z component of the orbital angular momentum. And then on top of that, you have the spin value also. And there are only two spin values. Either it's +1/2 or -1/2 as the basis states. Okay? And the total angular momentum, of course, is the sum of the orbital angular momentum, which is the angular momentum of the electron going around the nucleus, plus the spin momentum, which is impossible to to think of. You picture the electron as a tiny ball, and then it spins around its axis. But since the electron is not a tiny ball, this way of thinking is not quite valid. So, but all these results actually come out from the theory of the representations of the rotation group. Okay. But on an empirical level, what you have is the following: for a particular value of n, there are some L values that are allowed. L can go from 0 to n minus 1. Okay. So for this particular value, for example, of n, L can be just 0. Okay? Remember, it can go from 0 to n minus 1. If n is 1, then n minus 1 is 0. So that's the only value it can have. And then m, which is the z component, can go from plus L to minus L in steps of 1. But since L itself is 0, m can only be 0. Okay? Now, so it would seem that as far as the orbital angular momentum is concerned, there's only one state. Usually we characterize this by the triplet of numbers for NLM, 1, 0, 0, and that's it. Okay? But don't forget that there's spin momentum also, spin angular momentum also. And there are two possible values. So actually there are two different states, one with spin up, one with spin down. So that a degeneracy of 2. But it's equal to 2n squared, right? Because when n is equal to 1, then n squared is equal to 1, and so 2 times 1 is 1. So it's double degeneracy here, okay? Now, for n is equal to 2, L can be what? 0 and 1. Now, for each of these L values, M can go from plus L to minus L, right? So when L is equal to 0, M can only be equal to 0, right? But when L is equal to 1, M can be 1, 0, and minus 1, okay? So when n is equal to, so how many states are there altogether? How many states are there altogether? 1, 2, 3, 4. 4 states, okay? But then always times that by 2 because there's spin. So again, it's 2n squared. When n is equal to 2 squares, oh, wait a second. I have 4. Oh, 2 squared is 4. I'm sorry. 2 squared is 4. So it's 2n squared also. Now, when n is equal to 3, L can be 0, 1, and 2. Okay? Now, M for 0 can only be 0, but for 1, it can be 1, 0, minus 1. For 2, it can be 2, 1, 0, minus 1, minus 2. So therefore, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And you have to multiply it by 2, so that gives you a degeneracy of 18. Okay? But in any case, n squared is 9. Okay? So 2n squared makes 18. And you can go all the way up to as high an n as possible. Okay? The theory of the representation of the rotation group will give you all these results as far as the L is concerned, because L is a quantity that relates to rotation, to angular momentum. To get the values of E, we need a bigger symmetry, which is the one that we are talking about using SO4. As I said, in your regular quantum mechanics classes, you solve the equation, and then you remember how troublesome it was when you solve the angular part of the equation. Things come out very nicely. What were the eigenfunctions? You remember? Well, the eigenfunctions are the so-called spherical harmonics. Okay, those are functions on the spherical, on a sphere. In other words, functions of theta and phi. Turns out that the spherical harmonics are eigenfunctions of the angular momentum operators and so on and so forth. You can think of that way also. Okay. But the radial problem is quite complicated because of the special form of the Coulomb potential, which is 1 over r. And you recall that when you solve the radial equation, these strange beasts come up that are called, what kind of polynomials? They were called Laguerre polynomials and things like that, and so on and so forth. Okay, but in any case, it's a mathematical problem which involves partial differential equations involving separation of variables, and all those series expansion solutions, and so on and so forth. And you come out with the eigenvalues and eigenfunctions, and this is one of the results that's obtained, the spectrum, energy spectrum. Okay. We're going to try to show you how to derive this formula without using any differential equations at all. That is, only using the algebraic methods that are implied by the Lie algebra relationships of SO4. Okay? And so this is a completely algebraic method, which is not well publicized, at least not in the university curricula level. I'd say it's the best kept secret, okay, in quantum mechanics courses. I don't know why it's not introduced earlier. Maybe people just don't want to do group theory, okay? But historically, this was actually done before Schrodinger's work. Solving the hydrogen atom problem like this was first done by Wolfgang Pauli in about 1925. And it was only later that Schrödinger developed the Schrödinger equation and solved the hydrogen value problem by solution of the differential equation. And so there are these two methods, one using the analytical method and the other one using the algebraic method, that kind of corroborated each other. That was one of the historical reasons why people started to believe in quantum mechanics, okay? That you can either formulate it using the wave function approach, the so-called Schrödinger approach, or you can formulate it using the matrix approach. That's called Heisenberg's matrix mechanics. And later on, it was possible to demonstrate that the two completely mathematically equivalent to each other. So then, then quantum mechanics was on its way. Okay. All right. So let's see how to do this in the algebraic way. What I'm going to try to convince you is that in addition to SO3 symmetry, which is kind of obvious because the Coulomb potential is spherically symmetric, that there is a larger symmetry that is embedded in the Coulomb problem, and that is SO4. So I need to convince you that, that in fact there is this larger symmetry in the hydrogen atom problem, which is the SO4 symmetry. Okay. So let's start doing it step by step. First, let's write down, as in any quantum mechanics problem, you write down the Hamiltonian first, and then examine what kind of symmetries that particular Hamiltonian has. Okay, and then decide on what are the appropriate symmetry groups and so on and so forth. So for the hydrogen problem, let's say here's the Hamiltonian, right? P squared over 2m. Let's say m is the reduced mass of the electron. Okay, that is orbiting the hydrogen-like atom. And if the nucleus has charge z, then this is ze squared divided by r is the potential energy. Okay, there's one electron which is z, and then on the nucleus has ze. So the product of those charges is ze squared. Okay, r is the radial distance of the electron from the actually from the center of mass of the nucleus electron system. Okay, strictly speaking. But you already know from classical mechanics that two-body problems can be reduced to a one-body problem by factoring out the motion of the center of mass. And so this is basically the motion relative to the center of mass of the electron of the hydrogen problem. So you have a nucleus here, and you have the electron here. Okay. The center of mass is going to be very close to the nucleus because the nucleus is much more massive than the electron. How much more? Almost 2,000 times more massive. Okay. So you can almost pretend that the center of mass is right at the nucleus itself. But if you really want to be accurate, you know where it is. Okay. So this r is then the distance between the electron and the center of mass of the system, which is very close to the position of the nucleus itself. Okay. Now, let's say this is the quantum mechanical Hamiltonian, and you know that turning on the quantum key, pi, let me write as j, becomes what? It's not a variable anymore. It is h bar over I times partial derivative, the gradient, which is partial derivative with respect to the jth coordinate. Okay. So h bar over I dj, and we usually write it like this in our tensorial notation. Okay. Okay. Well, and r, of course, is to be absolutely clear about it. R is the square root of x squared plus y squared plus z squared if you use a rectangular coordinate system to define the position of the electron. Okay. So this defines the problem for you. Now, before we do quantum mechanics, let's go back to classical mechanics first. We saw that in classical mechanics, there's rotational symmetry, so the angular momentum is conserved. Okay, so the angular momentum is conserved But we also saw that in addition to angular momentum and the energy, of course, there's another thing that's also conserved, another vector. Do you remember what that was? The Runge-Lenz vector, exactly. Okay, Runge-Lenz vector. Let me just recall for you what that thing is, how it's defined in classical mechanics. In classical mechanics, the so-called Runge-Lenz vector, which we call M, is defined to be P cross L divided by M minus ZE square R vector divided by 1 power of the magnitude of R, like so. And we saw that in classical mechanics, this is also a conserved quantity. So there are the 3 components of angular momentum that's conserved, and there are also the 3 components of the Runge-Lenz vector that's also conserved, in addition to the energy. Okay? That's enough for the entire solution of the problem, because then this makes the problem what's called an integrable problem. The problem is done. Okay? You've found enough conserved quantities so that the problem becomes integrable, and so on and so forth. If you want to go through all the details, then you can write down the equations and find out the orbit, which in this case, classical mechanically, turns out to be an ellipse, and blah, blah, and so on and so forth. We've done all that in classical mechanics. And let's say that the problem is understood to be classically completely solvable. But now we're doing quantum mechanics, so things are a little bit different. How is it different? First of all, the PI is not just a number. The PI becomes an operator, a differential operator like that, okay? And if PI becomes an operator, a differential operator, the L's become differential operators also, because L is R cross P, okay? R itself is multiplication by a number, but P is a differentiation. So L becomes some differentiation also. And we have written down the differential expressions for the components of the different angular momentum operator. There's another problem when you try to quantize the system, okay? Quantizing the system means going from a classical expression for some dynamical variable to a corresponding quantum mechanical expression by turning on this quantum key, so to speak, so that your observables become operators. In particular, they have to be Hermitian operators instead, okay? When you turn P and L both into operators, a problem that immediately comes up is that P does not commute with L. Remember what commutation means? If 2 operators commute with each other, we write this by saying its commutator is equal to 0, which means that AB is equal to BA. Like so. 2 operators commute with each other when the order of the multiplication doesn't matter, okay? Now you know already that when you turn on the quantum key, then X does not commute with P. X does not commute with P. In fact, commutator of X and P, I can even put in the different components, right? Let me write this as KL. And there's a good mathematical reason for writing one of them is upper and one of them is lower. I won't go into that right now, okay? So one is in the tangent space, the other cotangent space, and so on and so forth. Do you recall what that is? IH bar delta KL, like that, okay? And in fact, this is the foundation, or this is a mathematical statement of the so-called Heisenberg's uncertainty principle in quantum mechanics. Okay, you can derive that statement that delta X, delta P has to be bigger than or equal to H bar over 2 from this mathematical statement in here. So that can be regarded as the uncertainty relationship. And when X does not commute with P, then P does not commute with L, because in L there's some X's in it. L is R cross P, remember? Okay? So when X does not commute with P, P does not commute with L. And if P does not commute with L, how do we know whether we should write it like that or write it like that? We don't know, because the 2 are not equal to each other. Okay? Now, classically, when P and L are regarded as just vectors, of course, you have P cross L is equal to minus L cross P, right? When they are just vectors. So you might be tempted to write an expression for the Runge-Lenz vector which involves the two different orderings of the P and L. Okay, so that both orderings are taken care of, and you kind of weigh them in the same, give them the same amount of weight, so to speak. Okay, now this is one possible way of quantizing the problem. Whether it's correct or not, you don't know until you've calculated all the results and compared with the experiment to see if it works or not. Okay, but the point is that historically this has been done by Pauli, and he found that it works, and so therefore, instead of writing it like this, I'm going to anti-symmetrize this expression by adding a term which is minus L cross P to it also, and then dividing the whole thing by half, okay? Like that. So quantum mechanically, we are going to give a quantum mechanical expression for M, write it like this. I'm going to divide this by 2 and then add this term, so I'm going to write 1 over 2m p cross L minus L cross P. Okay? And then put back the other one, the potential term, like so. Now, if L did commute with P, this is exactly the same as P cross L divided by M. All right? But the problem now is L does not commute with P, so that this thing is not equal to this thing. It's not equal, well, so that I should include the negative sign. So that this thing is not equal to this thing in here. And so we have to include both possibilities, so to speak, and give each one of them a weight of 1/2. Okay? So this is a guess, okay? And the thing then is to try to see whether this works out or not. As I said, Pauli was the first one that did that, and he worked out a lot of the algebra and so on and so forth. Although interestingly, he did not use the language of group theory to present the calculations. Okay. All right. Now, what's the next thing to do? The next thing to do, as I said, is to examine the Hamiltonian and see what kinds of symmetries are embedded in that Hamiltonian. So rotational symmetry is one kind of symmetry which is quite obvious. And as I said, there's got to be others also, okay? Because the result that we want to show is that there's going to be SO4 symmetry, which is bigger than SO3 symmetry, okay? In general, how do you, when presented with an operator form for the Hamiltonian, how do you decide what kind of symmetries it has? In other words, well, how do you decide? Let's go back to ordinary quantum mechanics. How do you decide whether there's rotational symmetry or not? To decide this, all you have to do is all you have to consider are just the infinitesimal rotations. In other words, all you have to do is to look at the generators of those infinitesimal rotations, which are precisely the angular momentum operators. Okay? So in general, how do you decide whether a Hamiltonian has rotational symmetry in general? And then see if the Hamiltonian commutes with that operator. You have to do this commutation calculation. Okay. Now, why is that? Why is that you have to do the commutation calculation? Because of the fact that in quantum mechanics, the basic equation of motion, the dynamical equation corresponding to the Schrödinger formulation is the so-called Heisenberg's equation of motion for a particular Hamiltonian, for a particular observable, Hamiltonian being one of them. So there are all kinds of physical observables like energy, angular momentum, positions and other things and so on and so forth, okay? So whatever the operator is, let's say you're given an operator A, which is formulated in quantum mechanics as some kind of operator in a Hilbert space, okay? Now, using a Heisenberg representation, this operator becomes a time-dependent operator. There's no wave functions to consider in the so-called Heisenberg representation. And all the time evolution is relegated to the operators. So this operator satisfies an equation, which is expressed in terms of the time derivative of this operator in here. And the equation is something like that. Now this plus dA dt, partial A, partial t. Now usually, most of the time, the operators that we are concerned with is not explicitly time dependent, so that partial A, partial t is equal to 0, but dA dt is not equal to 0. dA dt is governed mainly by the commutation relation between A and H. So if A, and this is called a Heisenberg's equation of motion. I don't know if you have seen this already, but it's mathematically exactly equivalent to the Schrödinger equation, okay? So if the Hamiltonian commutes with A, some operator A, then the equation says that dA dt is equal to 0, which means what? A is a constant of motion. So that means there's a certain symmetry in there. A is a constant of motion. So that to examine the symmetries, you just kind of take H and see what operators it commutes with, okay? And we will quickly find out that H commutes with both L and M. Commutes with both the angular momentum. In other words, H commutes with all the components of the angular momentum, okay, and all the components of M also. Well, let me write this back. L is equal to R cross P, where you express the components in terms of the components of R and P, and the components of R just x1, x2, x3, the components of P are like that, okay, and so on and so forth, okay? And so basically using this XL PK is equal to IH bar delta LK. This is a basic thing to begin with, okay? Then I can show that it's not too hard, not completely trivial, but it's not too hard to show that L, all the components of L, let me write it like this, LK, let's say, H is a scalar, is equal to 0. Okay? Like that. L involves both R and P, both X and P. You know how the commutation relations between X and P are, so that, and H involves P and X, okay, so that you can calculate easily, and you can show pretty easily that H commutes with L. When H commutes with L, that shows you that L is a constant of motion by the Heisenberg equation of motion, okay? Now, I'm here to tell you that MK, the different components of M, also commutes with H. Runge-Lenz vector as defined by this equation here, okay? I'm going to ask you to work these out as exercises, both this and this. This one is not that hard. You can do it maybe in 20 minutes. This one, it may take you a bit longer, depending on how awake you are, okay? It may take you a day or so, okay? But don't worry, I'm going to give you the solutions, okay? Now, to do the second one, you have to basically make use of this commutation relation, which can be derived from this one. Let me write down a commutation relation that is required. See, a lot of quantum mechanics is basically what? Calculating commutators, okay? A lot of quantum mechanics is about calculations of commutators. So this tells you how x commutes with p. Supposing I have some general analytic function of x, okay? I come in with a function, let's say a scalar function, which is a function of all the components of the x vector, which means it's a function of x, y, z, let's say, okay? An analytic function means that this is expressible as some power series in all the variables, okay? An infinite series, maybe, okay? Now, how does this commute with p? Obviously, we have to make use of some relationship like that because we need to be calculating weird things of x, right? This thing is pretty bad. It's 1 over the square root of x squared plus y squared plus z squared, okay? Where the x's don't stand in the numerator, like here. They stand in some function in the denominator. So how do we calculate it, okay? Have you seen something like this in quantum mechanics? How you calculate a commutator of some analytic function of x's with p? You may have, you may not have, but let me just tell you the answer, okay? This one is actually not too hard to prove. It is proportional to the gradient. It's a vector because even though this is a scalar, this is a vector, okay? And so, for example, if you want to calculate the commutator of fp with the jth, write down this lower, the jth component of p, this would be equal to I h bar dj or ddxj, write it more explicitly, of this function, like so. Okay. Maybe you should try to go home and prove that also. If you haven't seen it, that's not that hard. Okay. And using this, maybe then it will take you several hours to prove this, if you're wide awake. Okay. I think Pauli did that. Figure out how to do that. Figure out a neat way to do that, and so on and so forth. So we have six constants of motion. L1, L2, L3, M1, M2, M3. Because both L and M commute with H. We have 6 constants of motion. The 3 constants of motion, L1, L2, L3, follows from SO3 symmetry. Well, then the question is, how do these 6 constants of motion fit into an algebraic scheme? Okay. You know, you recall that when there was just a rotational symmetry, you had the commutation relations for the different L's as being given by something like that. We derived this, remember, from our general equation for SON symmetry. We just apply to SO3, and then we get this one, which is IH bar epsilon I j k. This I is not the same as this I, okay? I hope this is the imaginary unit. This one is just a tensorial index, okay? LK. Okay, so 1, 2 is equal to 3, and so on and so forth, because of the Levi-Civita symbol. Okay, so this is it. This is the entire story of SO3 symmetry, so to speak. This is the SO3 algebra. This is the Lie algebra of SO3, so on and so forth. Okay. Here we've got 3 more, M1, M2, M3. How do we make the 6 fit into a scheme? Huh? make it, well, how you prove? You have to prove that the commutation relations satisfy the general SON equation when applied to the case when n is equal to 4. We already know what the SO4 algebra is because we know what the SON algebra is. We did that last week, right? So the main thing here is to see that when taken together, these 6, L1, L2, L3, M1, M2, M3, follows the SO4 scheme, follows the SO4 algebra. All right? And of course, you know that it is going to, otherwise we wouldn't be talking to you now. We wouldn't be telling you that SO4 is the appropriate group, but it takes a lot of proving, okay? It takes you a lot more to show these other two commutation relations. So you have to find out the commutation relations between all the L's and all the M's, right? The L's themselves form a nice story because they are sitting on their own. They form a sub-algebra, so to speak, because they kind of work among themselves. When you take two different L's and try to make a commutator, it doesn't give you any of the M's. It only gives you back the L's. And so therefore, the L's form a sub-algebra, okay? Altogether, SO4 is a 6-dimensional. Oh, by the way, why is it 6? SO4? 6 independent values. You write a 4x4 matrix. 6 anti-symmetric, 6 independent values, and so on and so forth. Okay? So I have to figure out the commutation relation between the L's, between an L and an M. And then finally, I have to figure out a commutation relation between an M, one M and another M like that. Like so. Okay? Well, here are the answers. It takes a lot of proving, which obviously I'm not going to take the time to do it here, but I'm going to ask you to go home and show that, okay? Making use of these kinds of commutation relations and so on and so forth, okay? And then, now, let me write this down first and then discuss it. Divided by M, H, epsilon, I, J, K, L, K. It works out like this, okay? It's quite a nice algebraic exercise to try to prove that. And you should do it at least once in your lifetime if you want to study quantum mechanics, okay? Now, the interesting thing is this. L forms a subalgebra among themselves, but once when you throw the M's in, things got screwed up a little bit because the L and M together would give you some M, okay? But then when you throw the two M's together, it gives you back some L, okay? Now, the last equation presents us with a bit of a problem because it seems to give me something that has the Hamiltonian in there also. So it's not only the L's and M's. Normally, when you have a Lie algebra, you have a commutation relation between any two Lie algebra elements as a linear superposition of all the basis Lie algebra elements, okay? But then here, you know, these two are okay because the basis of this Lie algebra is L1, L2, L3, M1, M2, M3. So then, you know, this commutation just gives you back either the L's or the M's. But then here, it seems to give you something a bit extra, H, okay? But not to worry. Now, I haven't gone through all the theory of representation algebra of groups because of all the commutation relations. We say that because of the commutation relations H and L and M, we say that they are simultaneously diagonalizable, okay? That means a single set of quantum numbers can be assigned to a certain representation space. So if we are trying to find all the possible values of E, okay? And within each E, there's degeneracy, as we have seen, okay? So we can take a subspace, which is a representation space for SO4 also. And within that subspace, E has a single value only, okay? So we work within a particular subspace. Then I can just replace this H by whatever value it has to be, okay? E, in other words. H, which is normally an operator But if you work within a particular subspace, then you can work within that subspace, which is called the eigenspace of the Hamiltonian. And in that eigenspace, that Hamiltonian has just one fixed eigenvalue, which is E. There are many different eigenspaces, right, depending on how many possible eigenvalues there are. But we just work within one of them, since we're interested in finding what the possible values are in here. Like that. Okay, well, E is a number now. E is a number now, and all these guys, the L's and M's, are operators. Okay? Now you see that everything is nice, okay? L's and L's gives you L's, L's and M's gives you M's, M's and M's gives you back L's, so everything is, it's all one big family, okay? The L's and M's are one big family. It is a vector space, it's an algebra, it's called Lie algebra as SO4. Since it's a vector space, you can think of the L1, L2, L3, and M1, M2, M3 as the 6 basis vectors of that linear vector space. So everything in that vector space or everything in that algebra can be written as linear combinations of the 6 of them, which are, yeah.
So when, on the other part again,
yeah.
You read the Hamiltonian, is there anything you replace it with?
I replace it with a particular number, E.
Okay.
I know that the eigenvalues of the Hamiltonian are certain values, okay? And if I'm working within the subspace of all the possible space of eigenfunctions, the subspace which has a particular energy eigenvalue, I'm allowed to do that. Okay, then within the subspace, E has one fixed values, but the eigenvalues of the L's and M's may be different, just as in the case of the hydrogen atom. Within the same quantum state which has a particular energy eigenvalue, the L's and M's can be different, so on and so forth. Okay? Now again, I haven't gone through all the mathematical arguments to take us to that point, really, but I hope that we are trying to patch things up by your knowledge of what you've learned already about the quantum mechanics of the hydrogen atom, to at least be convinced that this is not so outlandish. This is a plausible thing that we can do. Okay, and that is to work within a particular subspace. Okay, there's a big Hilbert space, right? The Hilbert space can be divided into many eigenspaces, one corresponding to subspaces, one corresponding to each energy eigenvalue, okay? And I'm going to work within one of those, which has an eigenvalue equal to some number, okay? Right now, I don't know what that number is yet. When I'm done, I'm going to find out that all the possibilities are these, okay? By making use of the SO4 algebra, okay? Is that okay? So I'm working within one particular energy eigensubspace, all right? And all the operators L and M's and H's and so on are supposed to be operating on just the vectors in this particular subspace. So in this particular subspace, if V is a vector in that subspace, there's a particular eigenvector of the Hamiltonian in that subspace corresponding to a particular energy eigenvalue. Then everywhere I see an H operator, basically I can write it by E. Why is that? Because you know that H commutes with all the relevant operators, right? So let's say if let me think in terms of two operators, H and L, let's say. Two operators, okay? Supposing I want to find, supposing I have an operator which is like this, L1H, okay? Let me compare that with the operator HL1. But H commutes with L, so that HL1 is the same as L1H, okay? Now, normally, when you work out some expressions, you would see the operators appearing in their many different orders, okay, including these two, okay? And then normally what you would have to do is to find out the effect of operating using this to operate on some vector, which in quantum mechanics we write it using the so-called Dirac bracket notation like that. And we're going to see that because psi, let's say psi is an eigenvector of H, then this will be L prime acting on the vector which is the number times the vector like that. Since this is a number, I can write it outside, E L prime psi. I don't need to know what this is yet. Okay? But now let's look at the action of this on psi. But since L prime commutes with H, it's the same as this thing in here, exactly. Okay, so it's as if I can just write E in place of H like that. Why? Because H commutes with that other operator, which is the case here. Okay, so we can work within that one subspace, that eigen subspace of the Hamiltonian operator. Okay, this is roughly the logic that underlies that. Now, okay, in principle we have everything in here, but these things are, it appears to be kind of not quite convenient because of these ugly things like H bar and M sitting around and so on and so forth. So we're going to try to define things so that all the operators have the same physical dimensions. Okay? And this is rather easily done. What you have to do is to just do something like this. I'm now going to, L and M obviously do not have the same physical dimensions because of different ways they are defined. Okay? So I'm going to define a new M, which I'm going to M prime. And this is related to M simply by this manner in here. This is the original M. And this is a square root, which I write as minus, a little m is the mass of the electron. Now I'm working with a particular energy eigenspace, so therefore this is a number. And furthermore, I have to put a negative sign in here because I'm working with bound state, so E is negative. So that makes sense to put it inside of the square root, like that. Okay? So I have defined a new operator which is just proportional numerically to the original Runge-Lenz vector. We also call it the Runge-Lenz vector. Okay? This one is nicer because when you do that, then these guys appear to in much more kind of symmetrical form, if you will. The L's together with the M primes. The commutation relations can be written like that. The L's don't change. I H bar epsilon I J K L K. Second one, I'm going to write it in terms of Li and the M prime J. And when I introduce those factors, then some of these factors go away. There's only one power of M, so if I put M prime here, it's going to be the same thing. So the second one is not changed either. Epsilon I J K M prime K. Okay. Well, the third one appears a little bit nicer. M prime I, M prime J, commutator is equal to I H bar epsilon I J K L K. You see the difference between the two? This appears much nicer. Everything is dimensionally consistent, you see. L has the dimensions of what? H bar, right? But a commutator gets you to be square of H bar. And so it's right. There's two H bars in here. H bar in here. Dimensionally right? This one is also right, obviously, because M prime is whatever dimension it has, and then L is just one H bar in here, that's all. Okay? And you see, you can see also that the third one fits also. Here's a square of M prime. The square of M prime can be worked out by the definition of M prime, which we have just written down, and you can see that this equation just corresponds to this equation where we have gotten rid of these kind of ugly factors in there, okay, for the time being, all right? And now things appear in a pretty nice manner that these define some algebra. These commutations define some algebra. And the question is, which algebra does it define? And the assertion is that it's precisely the SO4 algebra. It's precisely the SO4 algebra. If I do the following. Now, you remember what the SO4 algebra was? Let me write it back for you in here. It's from the last chapter. So remember that we introduced the JIJs, those operators, those yeah.
I was just going to ask,
Yeah.
aren't the J's the basis vectors for our...
Yeah, the J's are the basis vectors for the Lie algebra. Each one of them is a vector, but each one of them in that particular case is a matrix also. It's a big N by big N matrix, depending on the dimension of the representation. Okay. And so there's 6 independent JIJs, and so let me write these in terms of the IH bar like this. It's anti-symmetric, so therefore it's like this. And so this one is J12, this one is J13, this one is J14, this one is minus J12 because it's anti-symmetric, this one is J23, this one is J24, this one is minus J13, J32, which is minus J23, and this one is J34, and of course here would be minus J14, minus J24, minus J34. So the only independent elements are these 6. Each of them can be thought of as a vector or as a matrix or whatever, okay? And we can think of them as matrices so that we can think of the commutation relations as commutation relations between different matrices and so on and so forth. And we're going to identify these in the following way with the quantities that we have introduced. In other words, our L's and M primes. 0, L3, third component of the angular momentum. This one is minus L2. This one is M prime 1. This one is minus L3. This one is 0. This one is L1. This one is M prime 2. This one is L2. This one is minus L1. This one is 0. This one is M prime 3. This one is 0. Minus M prime 1. Minus M prime 2. Minus M prime 3. And so we have these 6 independent ones in here. And you see how they are laid out? How they are laid out. Okay?
Why is there a minus sign on L2?
Because of the way you recall how the J's were defined in terms of the L's. Going back to the last, because of the anti-symmetry again, okay? The epsilon 1, 2, 3 again, okay? Okay. Now the idea is this. In the general case of SON, remember how we introduced these J's, right? And then we figure out commutation relations between the different J's for the arbitrary N SON groups. And I'm getting tired of writing this, but let me write it one more time. This is a general Lie algebra relationship. J, I, J, J, K, L. So it's a series of delta J's plus minus delta J's plus delta J's minus delta J's, K, J, I, L, I, L, K, J, I, K, L, J, K I K. I always think of Professor Kubo, I J K mu nu, alpha beta, blah blah blah, so on and so forth. Okay. Let's just try one thing, right? Let's try to relate the L's to the M's in here. Okay, let's try to relate the L's and M's. Supposing I pick 1, 2, 3. So let me pick L1, M2. Pick L1, M2 and see what happens. L1, M prime 2. Okay. Pick L1, M prime 2. L1, M prime 2. Is that okay? So what I need to do is to use this relation to show that L1, M prime 2 is in fact given by this and all the rest of it. Okay? If I can show that, this 3 are just nothing more than that one, apply to the case when n is equal to 4, then I'm done. Then I have shown that my SO4 is in fact a symmetry of the hydrogen atom problem. Okay. Now help me out here because it's getting late in the day, and so which two J's do we want to pick if I want to do L1 and M2? So let's pick these two. Okay, L1 and M prime 2. So let me pick the commutation of J23 and J24 in here. Okay, apply to the case when n is equal to 4. So let's do J23, J24. And now I apply this. So I, J, K, L have the values 2, 3, and 2, 4. Is that okay? Is that right? I, J, K, L. 2, 3, 2, 4. Okay. Here we go. Delta Kj, the first term. Delta Kj. Oh, that's gone because it's 2, 3. Okay. Second term is minus delta IL. 2, 4. Oh, that's gone also. Third one is delta IK. Oop, I'm in business. Delta IK is delta 2, 2. And so I'm left with J what? JLJ. J4, 3. Is that right? The last one is delta LJ. 0 also because it's 4, 3. So let's see if it works out. L1 is equal to minus IH, according to this way, okay. L1 is equal to minus IH bar J12, J23, right? And so J23 is equal to, so J23 is equal to 1 over minus IH bar L1. Is that okay? I is equal to minus 1 over I is equal to minus I, okay? So minus I is equal to I. So it's I over H bar L1. Did I make a mistake in here? Is that okay? This 1 over H bar. 1 over I is equal to minus I, right? So minus I is plus I. Minus I, M prime 2 is equal to minus IH bar J24. So therefore, J24 is equal to minus 1 over I h bar m prime 2. This is again equal to I over h bar m prime 2. Okay? Okay. And so apparently I have the two j's in here, so there are two I over h bars in here. J23 is proportional to L1, and J24 is proportional to M prime 2. Okay? Is supposed to give me what according to this? J43. Where's J43? J43 is this guy in here. Okay? J43 is this guy, which is minus J34. Minus J34. But J34 is equal to, again, I over h bar, m prime 3. I squared is equal to minus, well, let me cancel out one of the I over h bar. And so therefore I have, whoops, something is wrong. Maybe not, I guess. Cancel out one of the IH bars, so I have this. Okay? So when this gets to this side, it becomes h bar over I. Get rid of this in here. Finally, 1 over I is minus I. And so I have I h bar m prime 3. Works. H bar m prime 3. Okay? Because this is what? When I is 1 and j is 2, k can only be 3 in order for the Levi-Civita to not vanish. Okay? So in fact, this is equal to I h bar m prime 3. You should prove all the others also. You should go home. This is very easy. Now, this part is very easy. You prove that all these three are nothing more than this one in here when this equation is applied to the case n is equal to 4. Okay? So this convinces us that these operators, L1, L2, L3, m prime 1, m prime 2, m prime 3, can be considered as basis vectors of the Lie algebra of SO4. Okay? There's now, so what do you do? Okay, at this point. It's still quite some distance to get to here, which is what we really want, finally. Okay? Well, you look at SO4. It's SO4 is considered as a vector space. What's the dimension of SO at the Lie algebra? SO4 considered as a vector space? 6, right? These are 6 independent, L1, L2, L3, and m prime 1. And so it turns out that 6 is equal to 3 plus 3. This gives you a hint. 6 is equal to 3 plus 3. So the 6-dimensional algebra, it turns out, can be written as a direct sum of 2 3-dimensional Lie algebras. Okay? For other dimensions, this wouldn't work. Okay? 6 is just equal to 3 plus 3. So what we are trying to show now is that I can write this Lie algebra as O4 as being a direct sum of 2 3-dimensional algebras. Like so. We have to prove that, okay? But at least this makes sense dimensionally. One is 6 and the other is 3 plus 3. Now, what is meant by that circle plus? That this is, I think this is called a direct, we wrote it like this, it's called a direct sum. You know the concept of direct sums of vector spaces, right? So what is a direct sum of 2 vector spaces? Well, these two has to have one thing in common, which is a 0 vector, okay? And then, for example, the 3-dimensional space, right, can be written as direct sums in several different ways, right? can be written as a direct sum that's spanned by this vector. The direct sum of the vector space that's spanned by this vector plus the direct sum of the plus the vector space that's spanned by these two vectors, right? Or it can be written as the direct sum of this one vector space, or it can be written as the direct sum of three different one-dimensional vector spaces. So it can be written as z plus xy, or x plus yz, or y plus xz. So it can be written as direct sums in many different ways, as long as the dimensions of the different summons add up to being the same as the dimension of the original vector space. The only requirement, is that each of these has exactly just one element in common. That's a zero vector. Okay, right? It's clear. These three has exactly one thing in common. That's at the origin. Okay. Or the plane has exactly one point in common with a line. That's where they intersect, and so on and so forth. So then the next question is, how do I break up SO4 into a sum of two separate three-dimensional spaces? Okay. So to do that, I have to find a set of three basis vectors here, and then another set of three basis vectors here, so that together those form the basis of the entire SO4. Okay. And I can do it in this way. I can define 6 quantities. One is called L vector plus, and the other one is called L vector minus. Each one of these is a vector, so each one has 3 components. So together there are 6 components in here. Okay? And I simply define the plus to be a positive symmetrized sum of L prime and M prime. And this is the anti-symmetrized, so L prime minus M prime like this. Like this in here. Okay? It's clear that I can either use these 6 as the basis, or I can use the original 6. Sorry, the L and the M primes. The original ones are L1, L2, L3, M prime 1, M prime 2, M prime 3. I can also use L plus 1, L plus 2, L plus 3, and L minus 1, L minus 2, L minus 3. Is that okay? So you can use either set. But what makes this breakup possible is that I have to demonstrate that the commutator between these guys and the commutator between these guys are 0. They commute so that each one of them lives in its own subalgebra, so to speak. If you do it with the L's and M's, they all got mixed up in a funny way like this. Okay? I want to find something so that each commutes among themselves. So each one forms its own subalgebra, so to speak. So that this 6-dimensional algebra can then be broken down into a sum of 2 3-dimensional algebras. Okay? So what I want to demonstrate, which is quite obvious in fact, is that I have 2 subalgebras, one corresponding to the L pluses and one corresponding to the L minuses. And each one of them is a 3-dimensional algebra exactly like the SO3. Okay? So in other words, I have the following, which is very easily shown. In fact, I can write it all as one equation in here, L plus or minus 5 component in here, commutator with, the way to read this equation is that the top signs go with top signs and the bottom signs go with the bottom signs in here. Okay? Looks exactly like this subalgebra. Okay? So that this can then be shown to be I h bar epsilon I j k L plus or minus k. like so. Okay. Furthermore, the pluses always commute with the minuses, so they don't have anything to do with each other. Like that. So I've cleanly separated them. Okay. These guys, the pluses guys commute among themselves, and the minus guys commute among themselves, and the pluses and minus live in separate worlds. They don't have anything to do with each other. Okay? It's just thinking, it's best to think of this in terms of vector spaces. Okay? You can kind of carve up your vector spaces into different types of direct sums and so on and so forth, depending on convenience. Right? And it so turns out that that these commutation relations are very easily shown based on these. And one of the problems, again, is to ask you to do that, okay? Also, in order for these to be good ones, you have to show that either L plus or L minus commutes with the Hamiltonians also. But that's clear because all the L's and all the M primes commute with the Hamiltonians. So all the L pluses and all the L minuses must equally commute with the Hamiltonians. So they are constants of motions also. Okay? So they're constants of motion also. All right, I think we should stop here. I think we have reached a crucial stopping point. And next time we come back, we're ready to kind of wrap this up and then show you finally that energy. Or you can go home and read it in advance. So maybe it will make a little bit more sense. But this is a critical point. This is really the climax, so to speak, in a way, in a manner of speaking. That 6 is equal to 3 plus 3. It just happens to be that way. Okay. Maybe because he was Pauli. Maybe, oh, he had a hint, because it was known classical mechanically that the Runge-Lenz vector is a conserved quantity. So therefore, the jump is that quantum mechanically it must be a conserved quantity also. So he tried to write that formula for the M, and then it works.